from Princeton is going to tell you about extending NetKAT in a different way for supporting temporal logic kinds of operators. Is that better? Oh, cool. Okay, so this is joint work with my collaborators, Michael Greenberg. So software-defined networking has had a really major impact on the networking community over the past 5 to 10 years. And it's also seen very widespread interest and adoption in industry as well. And so really just this restructuring of the network so that you have a centralized controller machine which is responsible for programming and managing a collection of relatively simple and dumb network devices that are responsible for forwarding packets. And you can think of these presenting an API to the controller, which is very much akin to a kind of network assembly. It consists of simple match action rules where you match on packet headers and then apply some action like forwarding a packet's header or potentially dropping the packet. Once you have this restructuring of the network, it really gives you an unprecedented level of which allows you to do all sorts of interesting new types of. And so one prominent example of this is companies like SDN to do all sorts of interesting traffic engineering optimizations of their network for their wide area network, achieve utilizations of their network upwards of close to 100%. And so one of the key sort of challenges for programming language researchers in this area is to come up with new high-level programming language abstractions for the network and develop their sort of accompanying correct by construction methodologies and compilation algorithms, kind of, just like the previous talk we saw. And so far, the PL and networking community have done a really fantastic job in this respect. So they've built up all sorts of new abstractions on top of the network. So for example, one is routing of packets. So there are all sorts of interesting languages and compilers for doing packet routing. In addition, there are all sorts of languages and tools for performing debugging of your network where you might want to identify and then send them to the controller for logging or inspection by a human. There's also a bunch of interesting for specifying monitoring policies where you might want queries and then collect it and maybe aggregate it into statistics. And of course, last but not least, there's all sorts of interesting on your network. So there are tools like FlowVisor where you can dynamic security policy where you might, for example, drop packets that violate the security policy. And then there's also a number of verification tools where you can statically verify that your routing policy implements a spec. And so many of these languages have they might give you the ability to identify certain types of packets or paths that packets might take in the network. But on the other hand, they're usually implemented as disjoint systems. So you have one for routing, one for debugging, and so on and so forth. And so one of the sort of key high-level observations that we make in this work is that there's really sort of a shared underlying abstraction for many of these seemingly disparate tasks, which is namely the fact that if you could make dynamic forwarding decisions in the network based on a packet's history, so where the packet has been prior to the point at which you're processing it, code many of these tasks in a single framework. So with that in mind, I'll introduce the temporal NetKAT language, which extends the NetKAT programming language, which we just heard about, with temporal logic queries. And in the rest of the talk, I'll show how we can use that language to encode a number of these interesting tasks in an equational theory for this new language, and then prove that it's sound and complete for what we call. And then finally, I'll show how we can actually compile this language to switch forwarding rules, implementation, and show some of the performance. Okay, so let me give an overview of the NetKAT language itself. So for those of you who aren't familiar, NetKAT is tests, which is the algebra of regular expressions with very simple Boolean tests. You can think of over like. And this was extended in POPL 2014 to the networking domain by introducing primitives for. Right, and so the language falls into sort of these two separate parts. One as a Boolean algebra for matching packet headers, and another is a Kleene algebra of regular expressions for modifying packets and then moving them through the network. Right, so you can think of basically a packet. So the packet in this example arriving at a switch is just a record of fields and values, which might include that packet's location. So here we have a packet at a particular switch A, port 1, and then it might also have some other fields like a source IP, value of 10.0.0.1, and a destination IP, a value of 192.0. And then we have primitives in this language for matching and modifying the packet. So use Boolean combinators to match packets. So here we can ask if the source IP is not 10.0.0.1, or if the and then we can perform some actions. So we might want to modify the source IP to be a new value location, which has the effect of moving that packet across the switch. So this simple work lets you encode things like the topology. So you can think of a topology link as, in this case, switch A and port 2, and then moving that packet across the link to a new location. And then finally, you can combine these to get a network-wide policy by iterating, which has the effect of repeatedly applying these across the network. So what you can think about is going on in terms of that NetKAT policy is defining a function from a list of packets that corresponds to all of the intermediate states that the network, and it's producing 0 or more. So if you start with a packet that enters the network, it's just a singleton list of that packet, and then as you process the packet, you're going to accumulate all these intermediate states as it moves through the network. Right, and so the end result is that you have this final packet, which is at the head of the list, and the initial packet, which is going to appear at the end of the list. Right, and so of course in practice in networks, packets don't actually carry their history around with them. And in these existing programming languages for networks, you have no way to actually actively query the history dynamically in the network. So all you can do is observe sort of the topmost packet in the network, and this semantic mainly for reasoning about properties of programs in the meta theory. So the temporal NetKAT with these two additional, one which lets you test if it was true, and one lets you test if a predicate has been true since a taken from temporal logic. And so syntactic extensions to the language, but it has all kinds of different routing tasks, cascade of changes to the semantics, the equational theory, and the meta theory. Okay, so let me try to show you how you can think about the semantics of temporal NetKAT. So action that we could view the packet as having a history as it goes through the network. And so this is as if you could actively ask queries about the history whenever you want. So if you have a packet which is currently sort of the rightmost box in this diagram, and when it entered the network, it was. And so we can ask a question like, in the last state, was a field equal to a certain value on a packet? It's back in the history and checks whether or not that's true. You know, LTL is usually given in terms of an infinite trace, whereas here in the network, we're consider packets that are finite, these histories that are finite. And so a natural question that is no prior history, right? So what does this even mean to ask the question if in the last state a predicate was true? Trace semantics of LTL, which has been studied more recently, 2013. And the idea is that you're just going to define previous history. And so one of the interesting consequences is to identify the beginning of history by defining a predicate which we call start. So you can think of start as just saying you're looking to see if true does not hold in the previous state. And so this only happens in history, so when a packet is basically entering the network. And it's so we can also define which I'll use later in some of these examples. So here we have temporal logic diamond operator, which says which is just defined as basically true, and that has the effect of looking back through the history and seeing if that holds. And then additionally, we can define the dual of this, which is the always or box A predicate, which checks whether or not a predicate has always. Okay, so with that in mind, let me go through based on some of the earlier tasks I was motivating this talk with. So this includes debugging, monitoring, and so on. And I'll try to give an example for how you can do. Okay, so let's look at debugging and monitoring to determine the flows that are utilizing a congested link. To basically find out which packets are using the S1 to S2 link in this network. And we'd like to forward those packets to the controller so that maybe a human can look at them or something. We can take our original routing policy, which is just a NetKAT routing policy, and we can combine that with this plus operator, which basically just and what we can do is write a query which and then the dot here means and, so and at S2. And in the state before that, it was a copy of that packet and send it to the controller. Encode various types of security policies in temporal NetKAT. All traffic arriving at switch S6 has gone through both a firewall system. We can modify the policy so that the policy at switch S6 additionally tests if the packet has gone through the firewall at some point in the past and has gone through the IDS at some point in the past. And if it's not the case, then we can drop the packet, and that corresponds to sort of dynamically enforcing this invariant at runtime. Another example of a security policy is physical isolation of your network. So for example, you might have two different components of your network, and you want packets to either traverse one or the other, but never both. And so again, we can just take our original routing policy, and we can compose it packets so that we drop them if they haven't either traversed always basically one of these components. And then finally, we can pose problems of program equivalence in temporal NetKAT. Whether or not a network address translator is always modifying packets correctly by checking whether or not the route to that policy, where we filter for packets destination IP address equal to the new correct value, 17, ever since the packet went through the NAT. Okay, so there's sort of two interesting questions about temporal NetKAT. So one is with respect to reason. How expressive is this language, and can we reason? And then the other is for compilation. So how can we policies into switch rules, and can we scale this compilation to realistic topologies and policies? First question about reasoning about programs. So we introduce an equational theory for temporal NetKAT, which is based. So NetKAT has an equational theory which is broken into axioms, has Kleene algebra axioms, Boolean algebra axioms, and domain-specific packet axioms. We can actually just add on top of this a new collection of these finite trace LTL axioms that we developed. Axiom which relates a modification you make in a packet with a single step of time. So this says if you modify a packet, a predicate A is true. That's the same as testing A and NetKAT is a soundness and completeness theorem of the equational theory. Send that result to temporal NetKAT for a class of programs which we call so you can think of a network-wide program as a program where have no previous history whatsoever. Completeness statement by the fact that we're looking for programs that begin with the start predicate. In practice, usually these network-wide programs because associated with them. The completeness proof procedure using this equational theory. With that in mind, let me show how to rewrite temporal NetKAT terms. And so there's been recent work on language. The most recent and sort of the key insight automaton, so that as the packet goes through the network, if we want to answer it at a given switch, taking that information early, needing to keep the actual terms and splitting it into two parts. The temporal logic predicates in the term, basically free of any temporal logic predicates. A symbolic NetKAT automaton work. An example for compilation the details. So and routed across two switches. And the topology link as well. Is to basically be at switch B, and it's going to ask whether okay, so what we predicates from temporal logic as an abstract predicate in this. For this temporal predicate, which is going to we can basically see if the source is equal to x, then we move. The remaining policy where we just treat alpha so the trick then is we can actually do some progress you've made towards satisfying this query, as well as the value that we actually obtain based on the state we're in the symbolic automata to forwarding rules. This automata is a binary decision as one of these packet fields in this binary decision diagram. Structure, what you can do is you can generate these prioritized match action gives you the action that you would then perform to the packet. For the case with these temporal predicates. So we implemented a compiler for temporal NetKAT. Up 250 real network topologies. Also looked at the Stanford campus network, which is a mid-sized For each of these networks, we looked at several different types of policies. So if you want to do something as well as routing, so for example, or also maybe adding some temporal traffic that goes along a certain type of path, use traffic that goes from a number of different source locations, which could potentially detect denial of certain time as a function of the topology. The topology average compilation time in seconds on these separate lines. These policies that you want to do tend to have very low policy, which takes about 12 minutes to compile. Corresponds to a number of different intersection operations. Rules per switch on the y-axis. Tracking of history. So for example, if you want to is the most expensive with about a 2x over. We compiled the policies for the Stanford network. Compilation for this network takes between 10 to 14. And then finally, we looked at the relative rule over. For several of these queries, you incur almost no overhead at all. Of those isolated components without needing additional rules. Okay, so with that, let me wrap up. So again, we queries over a packet's history. This ends up being used to prove it's both sound and complete for what we call network-wide programs. Compiling the NetKAT programming language and show that it
You prove completeness for
yeah, good question. So actually, we think the opposite. A lot easier to prove it for the network-wide case, and that was the case that these temporal NetKAT terms in a way such for these two different axiom systems to potentially prove.
For checking, model checking LTL and CTL?
No,
I guess maybe to say it in another way, like to equal, like is there?
So we did not. I would guess that it is.
language where you can. History is really cool. Regular expressions are more expressive than temporal logic. I wasn't even sure if you. Those two automata have my program. Behind, depending on your perspective, from
What we ended up deciding was for all of the enough that we could encode it in temporal logic, but at the same time, into the regular language, you would potentially lose the